Well, hey, Mr. B here. Today's lesson's on chemical reactions and chemical bonding. Now, previously we talked about ionic bonds, and what I want you to remember from the periodic table is when we're talking about ionic bonds, we're talking about metals like lithium or sodium or any of these ones on the left side of the periodic table with nonmetals, and the nonmetals begin over here. Some famous ones: carbon, oxygen, fluorine, bromine, right? And you know a lot of those in their gaseous form. Today, we're going to look a little bit further than ionic bonding. This lesson is intended to look at covalent bonding, which is the kind of bonds that happen between things on the right side of the periodic table. It's shared bonding between the electrons of nonmetals. Okay, so let's roll. So when it comes to a chemical reaction, what we're talking about are, if you view atoms as cards in a deck, you can put cards together and make hands. Now, when atoms come together, and whether or not they donate electrons and then form bonds like an ionic bond, or whether or not they share electrons, you get new substances. Sodium and chlorine will come together, and we can take a look at that famous animation. Right, when we look at sodium and chlorine, you'll notice that the sodium kicks over its electron and chlorine is more than willing to accept it. Why? Because it satisfies the octet rule. Sodium, by getting rid of that electron, vacates its outer shell, and its inner shell has all the electrons basically fulfilling that shell. Chlorine, by getting the electron, well, it fills its outer shell. Now notice that sodium becomes positive and chlorine becomes negative, and they're of equal strength, equal and opposing strength, and they will just kind of come together, literally glue together, because one's positive, one's negative. And we talked about charges in one of my previous lessons and figuring out really what is the formula for an ionic compound, right? Today, this is about looking at electron sharing. Okay, so we'll go back here. So coming together and making new hands is really what we're talking about. Bonds are broken and created all the time. Some bonds are really difficult to break. Ionic bonds are the strongest. Covalent are next. Ionic bonds, if you think about sodium chloride, you think about salts. Those are extremely strong bonds. When we think about something covalent, oxygen is bound to itself. You've probably heard of O2 before, right? Or CO2, the gas we breathe out that helps plants with photosynthesis. Those bonds are a little bit different. Electrons are being shared, and the sharing arrangement isn't as strong as what happened in ionic bonding, where literally electrons were donated and accepted. What we're talking about here are making hands, rearranging things, and it's important to note that even when you burn something and you produce carbon dioxide, carbon monoxide, and you lose the carbon compounds that were in the log, for example, you've neither created nor destroyed anything. What's happening is the material is going from one form to another. Whether or not you can see it, it's a matter of measuring it. Okay. So when we talk about pure substances, we'd be talking about things like, let me just call up my pen here. Oop. We'd be talking about substances like NaCl, which I go on and on about, right? Lithium oxide. You could talk about H2O, CO2, and the list kind of goes on and on. I've just put up some covalent compounds, there's some ionic compounds, but these things have characteristics. For example, sodium starts out as a metal, chlorine starts out as a gas, and comes together to form a white granular salt. And it has, because it's come together, you've made a new hand, and salt has different properties than sodium metal or green poisonous chlorine gas, right? Two of the most poisonous things you can imagine come together to make something that we can't live without. And this is a new hand, new properties. So ionic compounds, just a quick review, right? We're talking about oppositely charged ions. Right? So we had cations, which were positive, and anions, which were negatively charged. So below, we've got the example of the sodium and the chlorine that we saw in the animation, and this is that lone electron that sodium doesn't want. By transferring it and giving it away, getting rid of that, its inner shells are full, and chlorine, by getting that extra electron, fills its outer shell, satisfying the octet rule. Now notice, this is a bit of a convention with Bohr diagrams. They've drawn the full Bohr diagram and they've put a positive charge there, okay? And they're putting brackets around it. This is a very formal way to do it. When you do Lewis diagrams, you don't have to do it this way anymore. You just focus on, if it was a Lewis diagram, you would have sodium like this, chlorine like this, just drawing the outer orbital, and you would draw the rest. But what we do when we conventionally, we just say this is sodium chloride, like that. Okay, so getting into covalent compounds, we're talking about nonmetals, okay? Nonmetals. O2, CO2, H2O, right? Carbon monoxide, the list goes on and on. Now, when you look at this arrangement, I know that hydrogen's an interesting one. We should talk about hydrogen for a bit. Hydrogen is the very first item in the periodic table, and it can be considered a metal or a nonmetal because it went first. Older periodic tables have put hydrogen on both sides of the periodic table. In the lesson today, as I talk about hydrogen, I'll be talking about it in its, basically in the context of it being a nonmetal. When you're the first thing in the periodic table, hydrogen was the first element that came into existence after the Big Bang, along with helium. And there's so much hydrogen in the universe. If you think about the fusing of nuclei, 1 + 1 = 2. So in stars, we're looking at a sun here, under gravity, that's a nuclear reaction which is pushing the nucleus of 2 hydrogen atoms together, and that makes helium. So hydrogen is the most unique thing in the universe. And everything after that, well, was created by fusion of nuclei, but somebody had to come first. It was hydrogen. So let's consider hydrogen in covalent lessons as a nonmetal. Now in this case, we know hydrogen's atomic number is 1, right? Go back there. So because hydrogen, its atomic number is 1, it has 1 proton and has 1 electron. Now hydrogen itself, having just 1 electron, the innermost shell, if you remember the 288 rule, this is the duet, right? In the very first shell, that shell holds 2 electrons. Now, because hydrogen has 1 electron, it's willing to make deals. It's willing to share its electron to fill that shell. In this case, what we'll do is we'll take a look at something like water. Hydrogen and oxygen. Water itself is a covalent compound, and it's pretty unique what happens here. Oxygen, let's go back to our funky periodic table. Oxygen has an atomic number of 8. So what does that mean? Well, from the standpoint, I'll just draw oxygen in the upper corner. I'll just say oxy like this. In its first shell, we put in the 2 electrons. And in the outer shell, 1, 2, 3, 4. See, we're up to 6, 7, and 8. That means that oxygen is desperately seeking a metal to either give it 2 electrons, and that's why oxygen will hook up with 2 lithiums, because each lithium will give up an electron. But in this case, if oxygen can find 2 electrons to share, then hydrogen is a really good partner. Take a look at this below, right down here. Okay, these are our electrons in the outer orbital. So for if we're just looking at the outside, there's our 6. And oxygen ponies up that extra electron right there. So what's happening is they're sharing. And it satisfies everybody's needs. Because hydrogen, for a limited time, will have 2 electrons in its outer shell. And oxygen will, for limited times, have 8 electrons in its outer shell, satisfying the octet rule. So that makes it pretty happy. And when we look at some of these compounds below, you can see water. And water is angular. It looks like Mickey Mouse. There's more chemistry to that. We'll talk later about that, especially when you get into Anatomy and Physiology 12. We talk about that in a lot of detail. You'll see the carbon in this compound here is sharing multiple electrons with oxygen. That's carbon dioxide. And if there's not enough oxygen available, like when you're burning wood in a wood stove and you turn the damper right down and there's very little oxygen, you'll get the formation of carbon monoxide. And that's when carbon gets a little bit more desperate and will form a triple covalent bond with oxygen. But more of this to come. So there's some things that we've already said, but are worth stating, that when it comes to chemical bonding, it's about filling the outer orbital. Now, today we're talking about sharing electrons, where previously with ionic bonding we were talking about literally donating or accepting electrons. And you want to fill up that valence, the outer shell. When we're talking about that, we're talking about the valence model, which takes us back to the Lewis structures, right? You want to have a stable octet. Sharing isn't as good as permanently having an electron donated to you like chlorine does when it gets it from sodium. Sodium is more than happy enough to give it away because that gives it a stable inner octet. Okay, so sharing is second best to just receiving, right? That's why ionic bonds are stronger. Ionic bonds are about satisfying the octet rule through donation, whereas sharing, well, you don't always have that electron. It's not as strong, but it's pretty strong when these bonds come together. When these two things come together, it's their valence electrons, right? The valence electrons are on the outside, right? So when we look at oxygen, and I'll do a quick drawing of oxygen here. Oxygen has, let's go like this. Now, what you do is you go to your periodic table, right? And you remember where oxygen is. So it is in the 16th column, and I always said pay attention to the last number there. 16. Okay, 6. The 6 is important because oxygen and sulfur and things in that column tend to have 6 valence electrons. So if I come back and I draw in 6 valence electrons, and I like to do the north, south, east, and west like this. And I'll just draw the 5th and 6th off to the side like that. Okay. So what does that mean? If you look, there are some lonely electrons down here at the bottom. And if they could just partner up like that, then this is the reason why oxygen double bonds. So I'll draw oxygen like this, and I'll draw a double bond like that. And because electrons repel a little bit, you tend to draw them, a bit like this, right? So they're sort of distancing themselves, social distancing for electrons. I know, bad joke. Now you'll see that what I did is I drew in what looks like an equal sign, but you have to realize what's there. There's an electron there, and we have an electron there, and we have an electron there. So I have to put those in. Now that you see this, I can just draw oxygen in a more simple way as like that. And of course, we can put in the valence electrons to be complete. Now, you need to understand that if there's an equal sign, at the ends of the stick, the electrons are there. Okay? So remember, there's one here, one there, and one there. You don't draw it in like that all the time. You just put in the lines. But now if you count, right? You got 1, 2, 3, 4, 5, 6, and because it's sharing 7 and 8, that satisfies the octet rule. And it's likewise for the other oxygen on the other side. So oxygen floats around as O2, and we say that is a divalent element. H2, O2, N2. We got a big old list to show you later. Okay, so ionic compounds. This is just a quick review slide. They're different because this is electron donation. So magnesium is an alkali earth metal, right? And this isn't sharing, folks. This is ionic. So magnesium is more than willing to give up those 2 electrons. It doesn't need these electrons here. It would be easier for it to vacate its outer orbital and to just give that to oxygen. This is why the formula MgO exists. Magnesium oxide. If you write in the charge structures, remember that if you lose 2 electrons, if you're a metal and you give up 2 negatives, you didn't lose anything in the nucleus, right? So that's why you are 2+. And because oxygen has taken on 2 more electrons, it's become more negative by 2, 2-. Because these are equal strength, it's 1 magnesium to 1 oxygen, and we just write that MgO. But I covered that quite a bit in my previous lesson. So we really like our Lewis diagrams because it simplifies these things. We can just focus on the outer shell, life is good, and we talk about fulfilling that outer orbital. We looked at, in the previous example here, this is a Lewis diagram because we're only looking at the outside, right? Okay. So let's take a few of these for a spin. Let's say hydrogen and fluorine come together. By the way, that's called fluoric acid. That's very strong. I wouldn't play with that. If they come into contact with each other and hydrogen's acting as a non-metal, what have we got? An ionic or a covalent bond. Well, if we're saying they're acting as a non-metal, non with non, sounds like a dish, then we are looking at a covalent compound, right? How many valence electrons does hydrogen have to even share? Well, it only has 1. And fluorine, well, take a look at fluorine. Fluorine is right over here, right? It's another poisonous gas. It's atomic number 9, and if you do the math, it's got 7 electrons in its valence shell. Well, so does chlorine, so does bromine. Remember, folks, these are in the 17th column. Now, remember that last number in the number 17 because it tells you how many electrons are in the valence orbital for these guys. These are known as the halogens. So, how many valence electrons does fluorine want to share? Well, fluorine has 7, and I'll tell you right now, fluorine's going to make a deal, but yeah, fluorine is out for that 1 electron. Nobody said that hydrogen and fluorine shared evenly, but that's a tale for another day. So, what does fluorine need from hydrogen? What kind of a sharing arrangement does fluorine need? Well, really, it only needs that 1 electron. That's all it needs. We can diagram this pretty easily. Hydrogen shows up with its 1 little electron, and fluorine, and always draw the lone electrons kind of facing in towards the middle. It just makes life a lot easier, right? Because we want a bond between the 2. And there we go. And if they share like this, then what you've got is, well, it's formally called fluoric acid, but you have a molecular compound here. And you might hear that sometime. They talk about molecular compounds. And when they say molecular compound, they're talking about these kind of bonds that we're looking at, right? These covalent bonds. So molecular compounds, covalent bonds. Okay. and I just wrote over top of everything there, but more or less, it represents what it's going to be. Remember that when you draw this, you draw H, F, and because it's sharing, all you have to do is put the electrons around fluorine. In this case, they're showing sort of a common fused side, but you'll see it drawn this way more often. Okay, so covalent compounds. What if we had a more easy way to visualize this? But now we saw this in the previous one, right? Hydrogen and fluorine, and here come the electrons, and the arrangement looks pretty good. Okay, so what if we take something else out for a spin? Let's take nitrogen, and kind of sort of think about nitrogen. Where the heck is nitrogen in the periodic table? Oh yeah, nitrogen right here is in column 15. Okay, think about the 5 in the number 15, and it'll help remind you that there are 5 valence electrons for critters in this column. So let's visualize that. Here they come. Okay. And because there's 5, what you can see is, well, heck, it just needs 3 more. Well, who could possibly supply 3 more electrons? Hydrogen is the most plentiful element, besides helium, in the universe. There's so much of it. It's the reason why you don't find a lot of free-floating hydrogen, because it's on all these chemical relationships, right? So hydrogen has its electron, and you think to yourself, well, okay, so how many hydrogens are going to show up and share with nitrogen? Well, it's going to take 3. And there's our sharing arrangement. Now, if you want to draw in the dots, right, just to remind yourself, here we go. So what does this do? Hydrogen satisfies its inner shell, its duet, and if you count all those red dots now that I've drawn in, you'll see nitrogen satisfies its octet, and it's pretty happy. That's why the formula for ammonia is NH3, right? The formula for fluoric acid is HF. So we've got carbon. All right, back to the crazy periodic table, I know. Sorry, I'm not trying to make you dizzy. Carbon over here, carbon always, a famous rule I always tell my students is, remember, carbon takes 4 bonds. Carbon is getting really, really, really close to, it's just a little bit away from the transitionary line between metals and nonmetals. But carbon itself is in column 14, which means, look at the number 4 and 14. It's a little pattern. It has 4 valence electrons. So carbon's looking for 4 more. You've probably heard of natural gas and that it's a renewable resource. Well, here's why. Even after carbon is burned and carbon goes into different sort of chemical states, carbon will do what it will share and do what it needs to do to satisfy its octet. It will find hydrogen and bond with it, and what you'll get are 4 of these. Now, again, I'm just being thorough. I'm going to draw in the shared electrons, and if you count everything that these carbon bonds are touching, carbon has its octet. It has 4 of its own. It's sharing 4, so there's 8. And hydrogen has satisfied its duet. Okay, so what's the formula? CH4. We call that methane. And let's be thorough. Okay, so when I was thinking about this lesson, what I wanted to do was take a few more of these out for a spin, just in a little bit more of a basic way. A couple of these out for a spin. We've got water, so let's draw hydrogen's valence electron here, and let's draw oxygen. It has 6, right? Double those up. And you'll see, okay, looking at this, it's not fulfilled, right? It's H2O. Oh, okay, so let's put another H facing this way with its electron. And now you'll see that this sharing here and this sharing gives you H2O. So hydrogen has a full duet and oxygen has, through sharing, 8 electrons, satisfying its octet. Okay, let's just make a little more space here. A more complex example, but it's a neat example, is carbon monoxide. Now, carbon monoxide is what forms when you burn, and when you burn a carbon compound and there isn't enough oxygen available. So in order to satisfy their octets, carbon and oxygen are going to have to come to a bit of an arrangement here. Okay, so what do we have? We'll draw carbon, and carbon has 4 electrons, right? Remember, it's in the 14th column, and the 4 and 14 is an easy way to remember that it's got 4 valence electrons. And we'll draw oxygen, and I'm going to draw it this way this time. Okay, there we go. So there are its 6 valence electrons. Now, you need to make pairs. So there's some obvious stuff here. If you draw a line between these two, you could make a pair. Okay, and if you draw a line between these two, you could make a pair. Now, it sort of looks like everything's fine from oxygen's point of view, but carbon hasn't got an octet. Carbon has 4, and it's sharing, so it's only really picking up 2. So, it's kind of interesting what happens here. Carbon, this electron, is just going to kind of sneak over here, and I'll redraw this. And then we'll draw what we had for oxygen there. And we had these bonds and these bonds. Now, in order to satisfy the octet, this sneaks over here and forms the last triple bond because they have to share something to both have an octet. So let's make this a little smaller because otherwise it'll take everything out. There we go. Okay. So what we have is a triple bond. So water is routinely written this way. It's a little bit angular, so I'm going to honor that here, right? There we go. Carbon monoxide is very much a straight line molecule, linear. So we'll do this. And then there's the electrons on the end. So that's a triple bond. Carbon monoxide is a really interesting one. We've already seen methane. Let's take a look at PCl3. Okay, and you're probably wondering, like, what is that, right? That's phosphorus trichloride. Okay, so what does that look like? Well, phosphorus, check the periodic table, has 3 valence electrons. And when you bring chlorine into the equation, it has 7. So let's draw our chlorines pretty close. And let's, remember it's a halogen, 17th group, right? And I'm just tight for space, but I can pull it off. And if you look at the bonds, what would it be? Would there be double bonds, triple bonds? Well, these single electrons pair up like this, and there you go. You have PCl3. Now, if you drew that, you would just draw like this, right? And then the outer electrons like that. And everybody's octet is happy and full. What about some of the divalent elements? Divalent, right? So things that float around in pairs. We've got H2 and we've got O2, right? We've got F2. Nitrogen does this. By the way, nitrogen is the most plentiful element in our atmosphere that plants are just dying to get at, but it's stuck in a gaseous form, right? Cl2. The list goes on and on. I'll provide a comprehensive list of the divalent elements. But if you take a look at halogens in particular, they like to go together in groups, and here's why. Halogens just need one more electron. So if you think about, well, why is it Cl2? Well, that's because chlorine will buddy up with chlorine. It's the exact same thing for fluorine. It's a match made in heaven. And boy, are they stubborn. They are equally after those that sole electron they need to fulfill their outer shell. So they share. And boy, that's like a tug of war where they're both pulling at the same strength. Oxygen. Well, oxygen will have, let's draw two oxygens like this. And I'm just going to draw the electrons off to the side. Now it's a little bit easier, right? And if you think about it, how many does oxygen have? You're up to 4. If you sort of go back to oxygen, you're like, oh, that's right. It's in the 16th row. It has 6. So we'll face those into the middle because it makes it easier. And I've just kind of angled the electrons away because I know they would do that. They don't like to be too close to each other. And there we go. So oxygen floats around and it's double bonded. Okay. Nitrogen. Nitrogen's another one of those interesting ones, right? So O2, nitrogen in the periodic table, right, is in the 15th row. So it has 5 valence electrons. So it's a bit kind of like carbon monoxide in a way. This will end up being triple bonded. I'm kind of giving it away. But 5 valence electrons. 1, 2, 3, 4, 5, 2, 3, 4, 5. And I've sort of drawn it this way so that the sole electrons, the missing ones, point in. It's easier than carbon monoxide because I can just straight shoot across like this, right? And that is a triple bond. So just drawing it, well, how we would normally draw it, we would draw it kind of like this, sort of quick. Right? And those are just, this is why you get these divalent molecules, because they satisfy their octet by sharing. It's all about sharing. Okay, so I'm going to go back to our slideshow for a second. I have to get back. Yeah, here we are. So when two elements are bonded together, it's called these are called diatomic elements. And here's your full list: chlorine, fluorine, oxygen, nitrogen, bromine, iodine, and hydrogen. Pretty complete group. And we've gone over this, just a quick animation going through what I had already previously shown, but there's oxygen coming together to satisfy its octet rule. And it does that through a double bond. Pretty slick. The way they drew it here, it's kind of a convenience. You're supposed to do electrons, kind of draw them a little bit angularly away like that, right? Just kind of as if they sort of moved off to the side, because there's a bit of natural electron repulsion. Okay, so a molecule is made up of 2 or more atoms bonded by covalent bonds. So when you say molecule, that means covalent. When you say ionic, you're supposed to say ionic compound. So that's sometimes a bit of a misnomer. I've caught myself talking about you're not supposed to say ionic molecule, for example, right? Molecular compounds are covalent. There's other ways to visualize these rearrangements. For example, here we're looking at water. So this is oxygen, which floats around as O2, and this is hydrogen, which floats around as H2, and then you get H2O. So you're sort of saying probably, where did that other oxygen go? And we'll be looking into something calling balancing of equations to account for where every single atom went. But these are three-dimensional structures, and it's really good to work with a molecular kit. There's some good animations online, and I'm going to try to put some of those at your fingertips so that you can do some of these rearrangements yourself. It really helps you to understand the three-dimensional structure of molecules. So I'm going to finish with this because this prefaces pretty much the next section. But when two hydrogens come together, a way of visualizing what they're doing, we had drawn it like this in our Lewis structure. Now, that joining, right, if we look at the outer orbitals, which is what's shown here, there's this overlap. And if you remember, these are sometimes called Venn diagrams. This is a way of showing that they're sharing within this space. Okay, same thing with fluorine right here with their outer electrons. They're sharing here. So if you overlap these here, just as you did up here, that's just a convention for showing the bond that they're sharing. How many overlaps of their electron orbitals are they actually having? So a few things to think about, right? Is it possible for a chemical reaction to occur without new chemical bonds forming? Okay, that's food for thought. Let you take that one out for a spin. And how much energy is required to make and break chemical bonds? Now, I'll just sort of set the table there with your thinking. Think about an ice pack. You have to break it and it gets cold. Well, okay, so why is it getting cold? What's going on inside the ice pack? Or you go out skiing and it's a cold day, so you break out one of those hot shots and pull it out of the package and you kind of squish it a bit. And then it's kind of an interesting iron compound in there. But instead of taking in heat, like the cold pack was, it's doing the complete opposite. It's giving off heat. Well, how does it magically give off heat? I want you to think about bonds. When you create them, energy is required. When you rearrange them, when they're broken, think about where the energy would go. Really, burning a log, right? All that heat and light. Where did that heat and light come from? Sort of creates it sets the stage for this next concept. But we're going to finish here, folks. This was a little bit of ionic bonding, but a whole lot of covalent bonding. Okay, cheers.